Today I'm going to be talking about post-quantum VDFs, basically VDFs that can withstand more scalable and powerful versions of these beasts. That's the IBM Q with 50 qubits. And like, one of the reasons why I'm interested in post-quantum VDFs and more generally in post-quantum cryptographic primitives is that in the context of Ethereum, we want to have a quantum roadmap for all the primitives that we use in Ethereum 2.0. Okay, so my talk will be in 3 parts. Basically, I'll give some context on the VDFs that we have today and why they're not totally satisfactory. And then I'll talk about the VDFs that we want. And then finally, challenges to actually getting to where we want to be. Okay, so first I'm going to talk about the VDFs that we have. So we have a bunch of pre-quantum designs, and most of the VDFs that we have are pre-quantum. So we have VDFs based on RSA groups, VDFs based on class groups, VDF based on Jacobian groups, and all these groups things, they all fall under this one bucket called groups of unknown order. And there's this quantum algorithm called Shor's algorithm, which is very good at finding orders of things. And so all these constructions kind of die in one go in the context of a quantum world. We also have a construction which is based on isogenies and pairings. Isogenies can be quantum secure, and I think that was one of the motivations for exploring isogenies-based VDFs, but unfortunately there's this pairing component of this construction, which means that it's not, unfortunately, quantum secure. And then we kind of, not a VDF, but still part of the wider randomness story is, of course, the threshold BLS cryptography, which is used in DRAND, which is used in Dfinity, and which is also not quantum secure. And to my knowledge, there's no quantum secure upgrade to that today. Okay, so that was for the pre-quantum stuff. What about post-quantum stuff? So we do have a few quasi-VDFs. So we have this notion which we call proto-VDFs. So the VDFs which have all the properties of VDFs, except that the verifier has high parallelism. So in order to verify the VDF output in a fast way, you need to have lots of hardware. And so this is the approach that Solana has taken. And basically the simplest proto-VDF here is a hash chain. So Solana uses a SHA-256 hash chain. It breaks down the long hash chain, which is the sequential evaluation, into baby chains. For each baby chain, they share a checkpoint, and then they send over the checkpoints to the verifier, who will verify each baby chain in parallel using GPUs, which have lots of parallelism. So that works great, except that the verifier, you need to have a verifier which is kind of expensive. And then a very similar idea is sloth, which is basically a slightly more sophisticated version than the hash chain. It's basically a hash chain where the hash chain is hard to compute in one direction and quite a bit simpler to verify in the other direction, but the asymmetry between the evaluation and the verification is only a constant factor, a factor on the order of, let's say, 100. So it's quite a bit of an improvement over hash chains, but in practice, the verifier is still too expensive. And then we have another basically post-quantum attempt at a VDF, which are called weak VDFs. So the notion of a weak VDF was defined in the original paper with VDFs, which defined VDFs as well. And basically, it's the dual to the proto-VDF. Proto-VDFs have verifiers with high parallelism, and weak VDFs is the opposite, is the prover that needs to be big. And so this is kind of problematic from a cost perspective because it's expensive to be big, but it's also not great for decentralization. And this is the approach that Starkware Labs has taken with their VDO proof of concept, which are actually live on the Ethereum mainnet today. And their approach is to use sloth, which is this permutation polynomial, and a post-quantum SNARK to basically take the easy verification of sloth and compress that whole thing as a big monolith into a succinct SNARK. So you can use different post-quantum, you can use your favorite post-quantum SNARK, I guess. You can use Stark from Starkware, you can use Fractal, you can use Redshift, you can use Spartan. But I guess, if you do this one-shot monolithic proof, then when your time parameter grows, your hardware will need to grow as well. And this is not just an academic point, it has real practical consequences where you're going to need machines which have hundreds of gigabytes of RAM and have tens of CPUs and things like that. Okay. I think the previous talks kind of went through sloth already. I'll go through it quickly. So basically there's the evaluation, which is hard, with, for example, taking a cube root in a finite field. If your finite field has n bits, it will take roughly n sequential repeated squarings to take this cube root. But verifying cube root is very easy. You just need to take that number and multiply it by itself 2 times. So you raise it to the power 3. And so you have this asymmetry between evaluation and verification. And sloth is basically, let's just have many of these asymmetric computations, and we glue them together with a little mixing permutation here. And so you see the evaluation in one direction is hard, but the verification in the other direction is several times easier. And what the VDO proof of concept design is that they took the easy side, which is, let's say, about 100 times easier than the hard side, and they tried to take that and compress it in roughly the same amount of time it takes to do the evaluation. So they compress it into a succinct proof, and they do this as a one-shot way using a powerful prover. So think some sort of server or like some sort of large machine on AWS. Okay, so that's the context in terms of where we are today. So I guess where we want to be is we want to be in a position where we have a quantum design, which is not really a quasi-VDF. It's neither a proto-VDF nor a weak VDF. It's like a real strong kind of VDF. And it turns out there's a small variation of VDO, the current VDO design, which is really nice and which achieves what we want. So instead of doing this one-shot proof of a very large statement, we're going to break down the evaluation into chunks. And so here we have 2 chunks, and we have a final proof. The goal is to get this final succinct proof. And instead of having a monolithic proof step, we're going to have many intermediate proof steps. So every evaluation chunk will have a corresponding proof. And this is in the context of what's called incrementally verifiable computation. So when you use it for VDFs, you could say it's an incrementally verifiable VDF, an IVDF. And the idea is that as you go along and you add more evaluation, well, your proof updates. And here, this proof here, for example, is a recursive proof. What does a recursive proof mean? It means that it proves that the evaluation here was done correctly and that the previous proof here verifies, which means that this evaluation was done properly and the previous proofs verifies, et cetera, all the way up to the beginning. And in order to have a chance, for the proof system, which is kind of heavy machinery, which has overheads, to catch up, to keep up with the evaluation, we use this slough idea, this permutation polynomial idea, where there's this asymmetry between the hard side and the easy side. So here we have the easy computation that is incrementally proved down to a small proof. And one of the interesting things is that this is actually the original design in the paper by Bonnet and Joe and Ben and the two Bens, Benedict, from 2018 that defined the notion of VDF. And so we're kind of going full circle. So we started with this design, which, at the time was impractical, and it probably still is, for a few years impractical. And we've explored the space with RSA, class groups and Jacobians and isogenies and VDO. And eventually we're going to tie back the loop and go back to this design. At least that's my prediction as things stand today. And one of the things that you might want to do when you're doing these recursive proofs in the context of quantum secure SNARKs is that you want to use these SNARK-friendly hash functions like Poseidon or Rescue or MIMC. And the reason is that often you'll be verifying these Merkle paths in the verifier circuit, and in order for the recursion to be efficient, you might want to use these SNARK-friendly hash functions, but you also want to use maybe a traditional hash function like SHA-256 for the very last proof, the terminal proof, so that it can be verified efficiently in CPUs and in contexts like the Ethereum virtual machine, the EVM. Anyway, that's a detail. So one of the properties of this really nice design, this iterative design, is that you have a pipeline prover where the proving closely follows the evaluation, and they move together in lockstep. So you have evaluation, which is broken down into chunks, and then you have corresponding proving chunks. And one of the things that you want for this design to work well in practice is that you want the proving to be at least as fast as the evaluation. So you kind of want a one-to-one correspondence in terms of performance between the proving and the evaluation. And so this poses some constraints on the proof system. You need to be able to do these proofs fast enough. Okay, and what are the kind of the benefits, some of the benefits of this really nice post-quantum design? Well, you have cryptographic benefits and hardware benefits. The two big cryptographic benefits, the first one is that this design is plausibly quantum secure. This is why we came here. And the other big cryptographic benefit is that there's no trusted setup. And trusted setups are really, really hard to do properly. And they cost a lot of effort and time and even money to do properly. So having to remove the trusted setup is a really appreciated thing in addition to the quantum security. There's also hardware benefits to this new design. One is that unlike VDO, which kind of is unscalable from a prover perspective, here you can have a fixed prover hardware which can handle arbitrarily large time parameters. So if you want to do the evaluation time, to do more evaluation, you want the delay to be longer, well, you just run the thing for longer and the thing just scales. And another benefit is that at least relative to the groups of unknown order, which can have quite large bit sizes in the modular arithmetic, slough can run with much smaller modular arithmetic, on the order of, let's say, 128 bits. And so that means that the hardware, your evaluator hardware that you're going to build is going to be cheaper, easier, it's going to consume less energy. So that's that's also a nice advantage to this approach. Okay, so we've discussed what VDFs we have today. We've discussed where we kind of want to be, or at least one really nice potential candidate, and kind of what are the challenges to getting to where we want to be. Okay, so one of the challenges, and it's an engineering challenge, is prover efficiency. So if you look at the numbers on VDO today, they suggest that if you want one randomness beacon, then you're going to need a big machine, on the order of hundreds of gigabytes of RAM and tens of CPUs. And as Kelly mentioned in the previous talk, if you have an Amax of, let's say, 100, then you're going to need roughly 100 randomness beacons to run in parallel in order to compensate kind of for the slowdown of each randomness beacon. So if you want randomness at a specific pace, then you're going to need to compensate with parallel randomness beacons. And there, if you have an Amax of 100, which is kind of a conservative number, but not crazy conservative, the numbers really blow up to tens of terabytes of RAM, thousands of CPUs, and it becomes too expensive with the technology that we have today to do it without optimizations. The other aspect of prover efficiency is the overhead of recursion, because these numbers are without recursion, and when you add recursion, there's going to be overhead for doing this incrementally verifiable computation. And at every step, you verifying a quantum secure SNARK is, let's say, roughly thousands of hashes in the verifier circuit, and it also means that your circuit will be much more irregular than with sloth. Sloth is essentially the simplest kind of arithmetization that you can get. It's the simplest computation that you can describe in the context of a SNARK. Once you have recursion, then things become more messy, and some of the tricks, performance tricks that you had, you kind of lose. So I guess there's two ways to address this prover efficiency. One way, which I'm optimistic could happen, is just with all sorts of optimizations at various levels of the stack, of the proof system optimizations, or hardware optimizations, like better usage of CPUs or GPUs or things like that. But there's also a big tool that we can use, which is basically to build a prover ASIC. And that would probably do the job. And one of the reasons the prover ASIC is exciting is that it would be a common good which is not only applicable to VDFs, but it's more generally applicable to speeding up these quantum secure SNARKs in general. That could be potentially a project for various blockchain foundations or companies to pursue, because it's a very neat and appreciated piece of technology that would benefit the ecosystem. Okay, so that's the first challenge, the prover efficiency. The other challenge that needs to be considered is the various assumptions that we're making. So this design makes cryptographic assumptions, for example, the Fiat-Shamir heuristic, which is very standard, and then it actually makes another assumption, which I call the recursion heuristic. And basically here, once you have a proof system with unbounded recursion, the soundness proofs don't really apply. And from what I understand, there's a decay of soundness for every level of recursion that you add, and you kind of need to wave your hands a little bit to say that it's secure, and hence the recursion heuristic there. There's also a hardware assumption around how much faster can an attacker be relative to the commodity hardware, basically the Amax. And I'll talk more about this later, and how this changes a little bit in our context. And we also have various cryptanalytic assumptions. We have these various we need these various hash functions to be secure. And we also have this sequentiality assumption of sloth, which, as it turns out, can be analyzed using the tools of cryptanalysis, things like Grobner bases and whatnot. So it fits in this category of cryptanalytic assumptions. Okay, so just to talk more about this sequentiality assumption, and it turns out that the Starkware team, as I understand, they haven't published it yet, but from what I understand, they found this GCD attack on sloth. And in order to patch the attack, they had to modify sloth and use kind of this state size 2 as opposed to using a state size 1, and that they believe removes the GCD attack. And I guess another interesting recent development is that if you take a generic model of computation in the context of RSA VDFs, then you can actually have really nice results that, for example, repeated squaring, speeding up repeated squaring is equivalent to factoring, which is kind of the best kind of result that you want in this generic setup. And the authors, these two authors are considering extending their results to things like sloth, which would be amazing. Okay, so now let me talk about the hardware assumption, the speed up assumption. So in the context of RSA, you have these really large circuits, millions, tens of millions of transistors. And it's hard to imagine that so-called exotic hardware or exotic processes could be used to tackle these very large circuits. But once you're dealing with smaller sloth circuits, the modular multiplication on the order of 128 bits, then exotic processes become a bit more of a worry, especially if we're talking 10 years into the future when we'll be deploying this quantum secure infrastructure. So there's things like gallium arsenide, gallium nitride, and carbon nanotubes, which basically take the semiconductor silicon and replace it with silicon 2.0, a new semiconductor, and you get transistors with new properties, which could have much higher speed. And so that's something you need to take into account in your attack model. And there's even more kind of exotic and sophisticated ways of doing computing, like optical computing, quantum computing, and RSFQ that also you need to take into account in your model. Maybe sequential equivalence to Grover's algorithm, for example, in the context of quantum, is I guess a possibility. So this is one of my last few slides, and I'm not sure if I have time left, but one of the other challenges is kind of the proof size and the soundness. So right now, in terms of soundness that's deployed in production today, we have 80 bits of conjectured classical soundness, and so that's deployed today with StarkX and Vidu. It's dealing with real money, and every time you want to upgrade the soundness, the proof size kind of increases, at least in the context of the Stark proof system. And really where we want to be is we want to have 128 bits of provable quantum soundness, which is going to come at roughly the cost of 8 times the proof size of what we have today, which is 80 bits of conjectured classical soundness under this very new conjecture which was made 2 months ago. And this is kind of the target for Ethereum 3.0. And this is my final slide, which I guess is an open problem for cryptographers. Can you design a VDF, a quantum secure VDF, which is based on lattices? And the reason why I highlight lattices is because the Ethereum Foundation is especially interested in lattices because they can do all sorts of crazy unicorn magic, like homomorphic encryption, witness encryption, functional encryption, program obfuscation. So this is an area we want to invest in. at the Ethereum Foundation. And I'm looking forward to researchers trying to tackle this problem.